So in the previous module, we defined a vector as something which transforms in the right way. And by right way, we mean something which transforms like a position vector or a velocity vector. And we derived the exact kind of transformation we expect of a vector. Just as a quick reminder, let's say we have the xy coordinate system, and I were to define the position of some point r here, which is, let's say, xi plus yj. And I would rotate the coordinate system to define a new coordinate axis, or new set of coordinate axes. Let's call those axes x bar and y bar. And let's say the rotation angle was phi. Then this position vector r, in terms of the new coordinate axis, would have components x bar along, say, I bar plus y bar, j bar, where I bar and j bar are unit vectors along the x bar and y bar axis. Now, the way x bar and y bar are related to x and y is given by a transformation rule, which we worked out last time, which is x bar, y bar is given by the rotation matrix cosine phi, sine phi, multiplied by the vector composed of the original components, minus sine phi, cosine phi, and xy. And so if we were to define a new quantity and we figure out that under a coordinate rotation, the new quantity, which has multiple components, transforms like this, like the position vector, which we've just worked out, then it's all right for us to say that the new quantity that we've defined is also indeed a vector. So we ended our last module with the question of whether the gradient, which is the del operator applied on a scalar function, is a vector. And the way for us to check this is to see whether if you were to perform a coordinate transformation, say a rotation by an angle of phi, does the gradient also transform in the same way like the position vector? Now, one of the things we need to keep in mind is that when we are talking about the gradient function, let me just call that a new vector. Let's say E, which is the gradient of a scalar function, and let's restrict ourselves to 2 dimensions. So let's say f is a function of 2 variables, x and y. Now note that f is a scalar function. By definition, a scalar function is something, or a scalar field is something whose value does not depend upon the choice of the underlying coordinate system. For example, if you were to measure temperature in a room and you go to some point x, y and measure the temperature there, the temperature will remain the same no matter how you lay down the underlying coordinate axis to measure the location of the point x, y. Which means that if I have a new set of coordinate axes, say x bar, y bar, the value of the scalar function f will remain the same as it was under the old coordinate systems, x, y. The only thing that will change is, of course, the vector del. So del in the original coordinate system was defined as composed of the partial derivative with respect to x and partial derivative with respect to y. These are the two components. And when this operates on the function f, you obtain the gradient. So the task for us is to figure out what is df dx bar, right? So these are the two components. So if I were to remove this f and operate it by these partial derivatives, we get the gradient function. So the two components we have are dou f, dou x, and dou f, dou y. If I were to perform a coordinate rotation, the two new components would be dou f. F remains the same, so I'm using the same symbol. Dou f, dou x bar, and dou f, dou y bar. So let's figure out what these two new components are in terms of the old components. Now dou f, dou x bar. Now remember that f is a function of x, y, right? So dou f, dou x bar can be written using chain rule as dou f, dou x, dou x bar, because x now, if you look at this expression, x bar is composed by mixing x and y components, right? X bar is x cosine phi plus y sine phi. Y bar is minus sine phi x plus cosine phi y. And I can invert this relationship to express x in terms of x bar and y bar, and y in terms of x bar and y bar. And we'll just do that shortly. So x itself is now a function of x bar and y bar, plus f is also a function of y. So it's df dou f dou y and dou y dou x bar. So we need to figure out these two components. And these are the old components of the vector. Now, in order to figure out how how we differentiate x with respect to x bar, I just write down the, I just expand the rotation matrix that we worked out last time. So x bar we know is x cosine phi plus y sine phi, and y bar is minus x sine phi plus x cosine phi. Now we all we have to do is just invert this relationship to express x in terms of x bar and y bar, and y in terms of x bar and y bar. And one of the ways, one very sort of straightforward way of doing that is just to eliminate the variables and just work out what x and y are. So let's say I look at this expression and I multiply both sides of this expression by, let's say I multiply this by sine phi. Then on the right hand side, we have x cosine phi sine phi plus y sine square phi. And I take this expression and multiply this with cosine phi. So y bar cosine phi is minus x sine phi cosine phi plus, sorry, this is y, plus y cosine square phi. And if I were to add both of these expressions, this plus this, you see that these terms cancel out, and I have y times sine square phi plus cosine square phi. So that's coming from the right hand side. Sine square phi plus cosine square phi equals x bar sine phi plus y bar cosine phi. But sine square phi plus cos square phi is 1. Therefore, we've figured out what y is. So y is x bar sine phi plus y bar cosine phi. So that's the first of our relationship. We have inverted the original equation and obtain y in terms of x bar and y bar. We can play the same game and obtain x as a function of x bar and y bar. And in order to do that, I'll again go back to this expression. And this time, instead of multiplying this by sine phi, let's multiply this with cosine phi. So x bar cosine phi is x cosine square phi plus y sine phi cosine phi. And I'll take this expression again, and this time multiply this with sine phi. So we have y bar sine phi is minus x sine square phi plus y cosine phi sine phi. And in order to eliminate these two terms and obtain x, what we now need to do is subtract these two expressions. So if I subtract these two, then on the right hand side, I again have x as a common factor. Cosine square phi minus sine square phi. The two terms get added to again give me x. And on the right hand side, I have x bar cosine phi minus y bar sine phi. And from here, we already have y equals x bar sine phi plus y bar cosine phi. So indeed, we have inverted the relationship. We have expressed x and y in terms of x bar and y bar. And now all we need to do is find out the partial derivative of x with respect to x bar and the partial derivative of y with respect to x bar. And then we plug it back into this expression. So I'll just rewrite this. So for dou f, dou x bar, we need dou f, dou x bar plus dou f, dou y, dou x bar. Now, what is dou x bar? So if I look at this expression and I differentiate this with respect to x bar, that is partial derivative, which means you treat y bar as a constant and just differentiate this with respect to x bar. So then we have dou x bar is just the derivative of this term with respect to x bar. So dou x bar is just 1, and that just leaves me with a cosine phi. For the second term, I need to look at this expression and differentiate this with respect to x bar. So we have dou y, dou x bar. And again, this term will go to 0 because we're treating y bar as a constant when we are taking the partial derivative. And when you differentiate this, you're just left with sine phi. And so we just go and plug these two terms back into the expression. So for dou f, dou x bar, that's the new component of the gradient vector in terms of the rotated coordinate system. We have dou f, dou x cosine phi plus dou f, dou y sine phi. So that's the first of our expressions. And in the same way, we can work out what is dou f, dou y bar, and that'll be dou f, dou x dou x, dou y bar, plus dou f, dou y, dou y, dou y bar. And if I look at these expressions, we need to calculate dou x, dou y bar. So you go here, you take the derivative of the left-hand side and the right-hand side with respect to y bar, treating x bar as a constant. And so we have dou x, dou y bar equals minus sine phi. So this will be minus sine phi. And when we go here, we need to differentiate this, partial differentiate this with respect to y bar, and we end up just with the term cosine phi. So we have here equals cosine phi. So overall, we find that dou f, dou y bar, the components, the new component of the gradient vector is the old component, dou f, dou x, minus sine phi, plus dou f, dou y, cosine phi. Now, if you look at these two expressions, these as the two new components which we have worked out, you see that they are exactly the same. They're given by exactly the same transformation rule as that we obtained for the position or the velocity vector. So if I just write this down in matrix form, we see that dou f, dou x bar as the first component and dou f, dou y bar as the second component equals, so the first term we have is cosine phi, then we have sine phi. So cosine phi, sine phi, then we have minus sine phi here, minus sine phi, cosine phi. And this matrix, that's exactly the rotation matrix that we worked out earlier. This matrix multiplies dou f, dou x, and dou f, dou y. And hence what we observe from this is that the gradient vector transforms in exactly the same way as we have seen the position vector transform. And therefore, our initial assumption or initial claim that the gradient is indeed a vector holds true. So I hope this was of some use and helps you build some intuition about the gradient vector, and hope to continue with this discussion again. Thanks for watching.